So there's actually more fun stuff in this section, but we're not going to do that until the next module, because there's quite a bit of stuff here, and I think the water pumping stuff is going to be kind of tricky. So we'll save the hydrostatic force for the next time. But let's do some problems. We'll start with 218, which hopefully should be pretty straightforward. Find the work done when a constant force moves a chair from 0.9 to 1.1 feet. Now there's two ways of doing this. There's the old basic physics way, which is work is force, constant force of 12 pounds, move something with a displacement of 0.2 feet. We can include units if we want. 1/5 of 12 is 12/5. That's 2.4, I think. But that's not the easiest way to do that calculation. Foot pounds. Now, of course, there's no calculus here. But you could also use calculus to say, well, we're integrating. Our x is going from 0.9 to 1.1 in feet. And our force function is 12. And if you do this definite integral, you're going to get the same exact answer. That's how it all connects. If something's constant, we can just use, Newton's law of motion. Or we can still set it up as if it were a variable function and just a variable constant function. Okay, so this is our f of x here. So it works both ways. You should get the same answer in both. 226. Find the mass of a metal rod that's 8 inches long. Right, draw a little picture. 8 inches long. Starting at x equals 0. So that's going to be x equals 8 over here. Density function, rho of x. Ooh. Rho of x equals e to the 1 over 2x. I think that's 1/2 x. E to the 1/2 x. Pounds per inches. Units are very important here. Make sure our units are correct, are consistent. Our density and our distance have consistent units. That's good. All right. And again, that means that at the start, when x is 0, our density is just 1 pound per inch. By the time we get to the end, our density is going to be e to the 4th pounds per inches. That's going to be more. We're curious about the total mass. Well, we know the mass is just the integral from a to b of the density function for linear density. Well, we want the whole rod, so x will be going from 0 to 8 of this density function, just like so. Now, we can use a u substitution here, or we can kind of do a little shortcut using just what we know about the chain rule and check our answer. If we take the derivative of this guy, do we get back to where we started? Derivative of an exponential function is itself, and then we have to use the chain rule to multiply by half. That'll cancel the 2, and yeah, we're good to go. That's going to be 2, and then e to the 1/2 of 8 minus e to the 1/2 of 0. This is not 0, by the way. We can't get rid of that. It's going to be e to the 4th minus 1, and that's as simplified as it gets. We'll have to use a calculator here. All right, 2 times e to the 4th minus 1 is 107.196. What are our units here? It's mass, and we're multiplying inches times pounds per inch. So I guess it's not technically mass, it's weight. 107 pounds. Wait, what? That 8-inch rod is over 100 pounds? I don't know if this is me making a mistake or this textbook being wacky. Hold up. 8-inch long has that density function. Is it supposed to be e to the 1? Is the x supposed to be in the denominator maybe? I hate how they wrote it. Integral from 0 to 1 of e. What if it's like this instead? Okay, good. Let's hope it's not supposed to be this way. I was thinking, I don't even know exactly how you do it this way if you did it, but we don't have to worry about it because it's not defined. So yeah. I think the book is just being silly right here. It's a really heavy material, okay? Huh. I don't think I missed anything. What? Oh, textbook, you're a silly goat. I don't think I'm messing anything up. Pounds per inches long. Okay. And again, we could graph this function if we wanted, just to really see that this is indeed correct. All right, we're going from 0 to 8 inches. And this is really where you're going to see it. Right. Look at the density. So this is the density function. This is how many pounds are in every inch on average. How high do we have to go to see this function? Yeah, by the end of the rod, there's like 8 pounds every inch. No, at the end of the rod, there's like 55 pounds per inch. The density at the end of the rod is insane. I wonder if they missed a negative or something. I don't know. This is what the book says. It's a dumb problem. Big rod. I'm sure there's material that's dense. Maybe it doesn't tell us how big the rod is. Maybe the rod is 8 inches, but like really, really thick. Like 8 inches of like Golden Gate Bridge suspension thing. I don't know. Anyway, it doesn't matter. But usually I tell my students that your answer should make sense. That's one of the benefits of physical application problems, but who knows? Find the mass of the two-dimensional object centered at the origin. A jar lid of radius 3 inches. Density function, rho of x, equals the natural log of x plus 1. All right, so this jar is, okay, a 3-inch radius jar lid sounds like it could make sense. And what are our units here? It doesn't tell us. So this is some kind of weight. Okay, so that's some sort of mass per inches squared. All right, so we don't know how heavy this jar lid's going to be. It's going to be some kind of units. Okay, but again, we know that we can split things up. We can use that formula that the total mass is going to be 2 pi times the integral. We're starting from 0, going up to that radius. And then, wait, I'm going to mess this formula up. I don't use this formula very much. I think it's just x times rho of x, right? X times rho of x for this. 2 pi x rho of x. Nice. Good. dx. The dx is important. You drop those, I might start taking off points. You never know. You should know. I should be consistent. And, ooh. Wait a minute. This is a good integral to use integration by parts on, which we don't know. This might be one of those integrals where you use a calculator because yeah, this is going to require integration by parts. You can do some sort of u substitution. That's just going to rephrase it into an integration by parts problem. I don't see a way to do this without integration by parts. I could be wrong, but either way, that's how you set it up. And then you could use a calculator to get your answer. I'm not even going to go bother doing the answer because they don't even tell us what units to do. But that's how you set this up. And that's how these radial disk mass problems kind of work. Let's do 239. These last two I'm hoping are kind of interesting. So a force, no, I didn't want to do 239. I changed my mind. I changed it to 237. I just didn't update it in my notes. 239 is pretty basic. 237, I think, is more interesting. A spring requires 5 joules to stretch the spring from 8 centimeters to 12 centimeters. All right, so 5 joules, you go from 8 centimeters, 12 centimeters. And an additional 4 joules, that's going to be 9 joules total, go from 8. Wait, an additional 4 joules. Oh, I think it just means 4 then. I think the wording is kind of weird. 4 joules to go from 8 to 12. So, oh, from 12 to 14. I think I'm interpreting this correctly. What's the natural length of the spring? So this is a bit of a tricky question. But the idea is if we can put everything in terms of what we've talked about, we should be able to find this. Okay? So let's look at each piece of information. Remembering that work is the integral from A to B of force times, well, it's force times distance, so it's the integral of just the force. And we know that force, right, for a spring is kx. So in this case, we know 2 pieces of information, red piece and blue piece. Red piece says that 5 is equal to the integral from, so now this is where you have to be really careful. This does not start at x equals 8. It's stretching the spring from a length of 8 centimeters to 12 centimeters. But if I wrote x equals 8, remember our spring diagram. I don't know how far it is. X equals 8 means that this is 8. This is x. But we don't even know where rest is. Okay, and that's the precision of this problem that I think the book is going for. I hope it's going for this. Okay, so it's not going to be from 8 to 12. It's going to be from 8 minus whatever the length of the spring is, the natural length of the spring is, up to 12 minus the natural length of the spring. It's not going from 8 to 12 at all. So the natural length of the spring is 4. It's going from 4 to 8. All right, and that's the subtlety here. Of again, just kx dx. And then we have the blue piece as well, which says that 4 is the integral from now 12 minus L to 14 minus L kx dx. So solve for L. K shouldn't matter. Maybe K will matter. We'll find out. Let's solve for L. So the antiderivative is K over 2, x squared evaluated from 12 minus L. The 14 minus L. I have no idea where this is going, by the way. I just picked it because it looked fun. Let's see where it goes. So if we simplify this, we get, let's multiply both sides by 2 over K, just to make things a little cleaner. That means we get 8 over K equals x squared, 14 minus L squared, minus the other one, 12 minus L squared. And when we simplify this all out, hopefully we get something useful. 14 squared is 196 minus 28L plus L squared. And then we're subtracting 144 minus 24L plus L squared. So we have a plus L squared. We have a minus L squared. we have 199 minus 144, that's 52. And we have negative 28L plus 24L is minus 4L. Great. We have an equation with two unknowns. That's okay. We have to do the same thing for the red guy. So, by the exact same logic, we're going to get 5 over k. Sorry, 10 over k. Got to be real careful about taking shortcuts. 10 over k going to be 12 minus L squared minus 8 minus L squared. Again, I want to box this. This is going to be important. This is not our final answer, but let's not box it. Highlight it. We need this later. Let's find information over here. So 10 over k, let's FOIL again. Just like before, it's 144 minus 24L plus L squared. We're subtracting 64 minus 16L plus L squared. L squareds cancel again. 144 minus 64 is 80. And then negative 24L plus 16 is minus 8L. So this is the second piece of information that we're using. So if we can solve for k, then we could set the k's equal to each other and get rid of that way. Or we could use the elimination method, actually. That could maybe be a little easier. 8 over k is 52 minus 4L. Yeah, I think solving for k is actually messy here. The elimination method is going to be easier, I think. So if we just multiply this, if this is 10 over k, then we're good to go. How do we make this 10? We can multiply by 10/8, which is really just 4/5. Sorry, 5/4. We multiply both sides by 5/4. We get something really nice. We get 10 over k is 65 minus 5L, I believe. I'm doing a lot of math in my head, guys. And now we can subtract these two things from each other. Let's take red minus blue. Red minus blue is going to give us 0 equals 80 minus 65 minus 8L plus 5L. This is red minus blue. Oh, L's 5. We did it. 3L is 15, L is 5, and our units are centimeters. So the spring is naturally at 5 centimeters. Now, before I check my answer with the book, I want to check my answer in a more interesting way. If L is 5 centimeters, are these two things true? Let's look at that. So, is the integral from 8 minus L to 12 minus L, again, L is 5 here, we don't know k. We can't check our answer this way, I guess. There are some ways that we can still check our answer. We could like choose an arbitrary k and see if this relationship is the same. But yeah, I guess we can't do it as easily as we might want. Let's check our answer with the book. I feel good about this, but it's a good habit to get into to check your answer. This is 237, 5 centimeters. There it is. Okay. So I want to do this one because it uses the calculus, but the problem solving method is a problem solving method. It's not just plug and play. You have to actually figure out how to set it up and what to do. Most of it's just solving a system of equations. And again, to just reiterate something like this, if you have information, try to format that information into the language or the context of what we're doing. And that's the really tricky part in this problem and why I wanted to do it for y'all. All right, the last one should be fun as well. I think that's the swimming pool. Maybe not. Nope. It's not 245 either. I updated that as well. 245 is not that interesting. I mean, it's kind of, it's another force equation. It's kind of interesting, but I want to do something more different. I do 250. Pump water out of swimming pool if the area of the base is 800 feet squared. Oh dear. Wait, what? All right, so it's a we don't even know what the swimming pool looks like, huh? But we're assuming that it's some sort of regular figure. Many swimming pools are rectangular. Let's just think of a rectangle swimming pool. All right, and we know the area of the base. This is 250. You know the area of the base is 800 feet squared. Wait, I just lost the problem. Oh, it's because it's doing this thing. I have to refresh, otherwise every time I alt tab, it's going to move my screen. 250. Great, that's what I wrote. The water is 4 feet deep and the top is 1 foot above the water level. What does that mean? It means the swimming pool itself is 5 foot deep, but the water is only a depth of 4 feet. Yep. Yep, water is 4 feet deep. Top is 1 foot above the water level. And assume, so 62.4, not 42.4. 62.4 was our assumption in the last one. Here, it wants us to assume that it's going to be we'll just make it a nice 62 pounds. Whoop, that's not you. Wait, pounds. Wait, that looks so wrong, but that is pounds. Pounds per feet cubed. Weird. LB. Why does that look so wrong? Silly imperial units. Okay, so now we just do all the steps that we did before. Okay. So we drew our picture. That was step 1. Now we draw our little mini picture. That'll be step 2. And says that at any height, right? At any height. Oh dear, that is terrible. At any height, what does our little slice of water look like? Okay. So we need to move it X to the top. X is going to be how far it is from the top. And we have this little rectangular slice of water. Okay, this is better, right? With height delta X and air. We don't know the dimensions. We just know that the area of this slice is also going to be 800 feet squared. So the volume of this little guy, I'm going out of order, is just 800 delta X. Right? And it needs to go X units up. X feet up. Okay, well, we're looking for the total work. The work of any piece is just the force times the distance, and the distance is going to be the X distance for that piece. Again, technically, these all have I's here. Well, the force is the weight of water. That's just going to be the volume times the density of that water. Volume is 800 times delta X sub I. Density is constant, 62. So the work is just the force, which we found. What's 62 times 800? $49,600. I wonder if I'm skipping a step. This is what happens when I try to go fast. Well, I'm not trying to go fast. I just want to do it chronologically. Work is force times distance. Force is the weight of water, which is the volume times the density. Got the density, got the volume, multiply them together. That's the force. And we just add up all of these. That gives us a Riemann sum. The total work is just going to be the integral. We're starting at a level of water that has to go 1 foot up to get to the top of the pool. We're ending at the bottom of the pool, which is when we have to move the water 5 feet up to get out of the pool. And then we just have 49,600 times x. The delta x becomes the dx. And that'll be our answer. There's just 49,600 times x squared over 2 from 1 to 5. That's going to be 2, 4, 8. Who do we appreciate? I think that's it. Multiply that by 2. You know what? Let's not mess around. 49,600 divided by 2 is 24,800. Great. All right. And then 5 squared minus 1 squared. That becomes 24. So what is this times 24? 595,200. And this is in foot-pounds for the work. That much work to get all that water out of this pool. So if this were, this, you know, maybe this pool is, 40 feet by 20 feet or something. Yeah. Okay. Not a very big pool, but that's how much it's going to take to pump the water up to the top. And that's pretty much what we've got here. This is an even problem. I can't check my answer with that. Let me know if you see anything. Best of luck, and hope you enjoyed this section because there's more of it in the next module. Bye-bye.